Today's lesson is on power functions, and this leads us off into many different relationships amongst functions, rational functions, polynomials. This is a very important chapter as we wind up the semester, and we only have really only two more topics that we're going to talk about outside of this chapter. So it's getting down to the end. So first of all, what is a power function? Well, a power function is either directly proportional or indirectly proportional. Here are two examples. The area of a circle is pi r squared. Well, this is a directly proportional function, but it is called a power function because it is in the form a constant, a variable, and a power. Okay? Now this one, example 2, is inversely proportional because it's a division problem. So it's a constant divided by a variable squared. Now it doesn't have to be squared. It can be any power. Okay? But the power, we're used to seeing this. But that's not what we're talking about. We're going to talk about that, or this, or x to the 6th, or x to the 8th, or x to the 9th, or x to the 1/3, negative 1/3, things like that. Okay? So that's what we're dealing with in this chapter. And here are what I was talking about, what we call the power functions. If it's directly proportional, it's k times x to the n. If it's indirectly proportional or inversely proportional, then it's k over x to the n. But they all can be written in this format, kx to the p. P is a constant and so is k. So the variable now is our base right here. So these are not exponential functions. These are called power functions. Now, on example 3, we're going to look at which ones of these are power functions, and if they are, see if you can figure out what k and x are, or k and p are, I should say. Well, if you look at number 1, we can rewrite this as 13x to the 1/3. By doing so, we have now created kx to the p. Have we not? So our constant is 13, our power is 1/3. On this particular problem, you can't make this just x. So this is not a power function. That does not work. So we can't add or subtract anything to it. Now we're looking at C going, whoa, there's no way that can be right. Well, let's just see a moment. Let's rewrite it like that. Let's break it up into square root of 25 over the square root of x cubed. But remember, the square root is 1/2. So that's 5 to the over x to the 3/2. Oh, look at this. That's 5x to the negative 3/2. Guess what? K and P. So that is a power function. Doesn't look like it, but it is. Now, this one obviously is not, because our variable is the exponent, and that's not how the power function works. The power function, the exponent, is a constant fixed number. Here it is not. So that's just an exponential function, which we've already talked about. Now, the effect of the power p. So if I just go x to the 0 and x to the 1, those are both linear functions. X to the 0 is just 1, so y equal 1 is a horizontal line. And then y equal x to the 1 is just y equal x. It's just the line, which is up 1 over 1, up 1 over 1, etc. And they do intersect at 1, 1. But that's just a special case. It is a power function. We just really don't focus on that very much. Now here's where we focus. Look at the positive even powers, x squared, x to the fourth. If we keep going, x to the sixth is going to look like this. X to the eighth is going to look like this. Just gets fatter and fatter, wider and wider. But they're all what we call U-shaped. And now they're not parabolas. They are just U-shaped. All positive even powers are U-shaped. Now, all odd powers we call chair-shaped. They have this little squiggle going on, like so. Now, they may do this. That's okay, too. It's still a chair function, okay? So odd and even powers, positive, okay? Now, negative powers. Well, you can see that x to the negative 1 is goofy. But remember, that's 1 over x. And that's what we call basically a hyperbola. It's really weird, but that is the graph, okay? Now, x to the negative 2 looks like this, and which is 1 over x squared, if we wanted to write it another way. But that is this graph, and I always call this just like a volcano. So then you can take your calculator and graph x to the negative third, x to the negative fourth, and explore those negative integer powers. You're going to see that they're very similar to these two. Now, the effects of the fractional powers. Okay. Remember, x to the half is the square root of x, and x to the 1/4 is the 4th root of x. X to the 1/6 is the 6th root of x, and so on. Well, none of those cross over into the second or third quadrants because they don't exist. So they keep getting higher like this, and they keep doing this, and they keep doing that. So you can see that they're very similar graphically to each other. Same way on the odd fractional powers, 1/3, 1/5, 1/7. They're a chair function, but they're tipped on the side, as you can tell. You can see there. Okay, now that is the entire lesson. So on page 439, we are going to look at 3 through 13, 15, 18, 19, 25, and 26. And I went ahead and did 13 for you. So let's look at 13. This is much like we did with AB to the T, but now it's KX to the P. F of 1 equals 3/2, and F of 2 equals 3/8. Thus, the points are 1 3/2 and 2 3/8. We're going to do these just like AB to the T problems. So we have 3 over 8, so you always put the 1 on the right first. 3 over 8 equals K2 to the P, because it's Kx to the P equals F of x, okay? And then 3/2 equals K1 to the P. Now, the K's cancel. 1 to any power is 1, so we can get rid of that. 3/8 divided by 3/2 is 3/8 times 2/3, because we're multiplying by the reciprocal. The 3's cancel, 2 goes into 8, that's 1/4. So 2 to the P equals 1/4. Well, 1/4 is 2 squared, 1 over 2 squared. I can move this up and make it 2 to the negative 2 equals 2P, so our P is negative 2. So we have our P. Now we need our K. Well, I'm going to take the first one, which is 3/2, and I'm going to change that x to a 1. 1 to any power is 1, so there's K. K is 3/2. So our equation then is 3/2 x squared that will go through these 2 points. That gives us the power function that fits those points. That's the power function, 3/2 x squared. You'll also do 15 this way as well.